Alright guys, for whatever reason the video did not record my audio this morning in class, so I'm going to just briefly review the notes. If you have any questions over it, I'm basically wanting to get the digital version of the notes online, but if you have any questions on my explanations, feel free to stop in and ask some more. Chapter 2 is limits and continuity. I first started off by defining calculus as being the mathematics behind looking at a curved system using an infinite number of linear functions, and then I'll give an example of, if we draw this parabola, well, we've got two different kind of lines that relate to that parabola. We have tangent lines, which are lines that touch at just one point, and we have secant lines, which pass through the parabola. And any kind of curved function can be created by drawing an infinite number of lines that are tangent to it. So, with that said, one overarching concept in calculus is how do you find the slope of a curved object? And then I showed this example of the hill. If we have a hill that we're traveling on, and we want to find the slope of a curved object, or we want to find the slope of the hill at this point, well, we can't do that with basic linear algebra because in order to find the slope, we have to have 2 points. So, we can't do this, find the slope of the tangent line because it's only 1 point, we need 2. We can find the average slope of the entire hill, taking the lowest point of the hill and the highest point of the hill, because now that's a secant line, and secant lines have 2 points, so therefore we can use the formula for slope, which we'll get to here in a minute. Before we get to that, we want to go over some function notation. Y is equal to f of x. 3 equal to f of 2 is the same as the ordered pair 2, 3. Graphically, if I asked you what does f of 1 equal, that's x is 1, so you find 1 on the x-axis. The y value that corresponds, that's 2, so f of 1 is equal to 2. And then algebraically, if you're given a function, say x squared plus 6x, and I ask you to find f of negative 2, you just plug negative 2 in for x in both spots. Negative 2 squared is 4, 6 times negative 2 is negative 12, 4 and negative 12 make negative 8. So that's how you would do function notation algebraically. Briefly, I'm going to go over the formula for slope given 2 points. You can see that, the slope between them, also known as the average rate of change, can be found by y2 minus y1 over x2 minus x1, the same formula you've always used. In calculus, though, we're going to switch this to function notation. So given 2 points, a comma f of a and b comma f of b. The average rate of change is f of b minus f of a over b minus a. Same exact formula, just using function notation. And then we discussed that the average rate of change is finding the slope of a secant line. And we did an example, and I asked you to find the average rate of change of f of x equals x squared plus 2 on the interval, negative 1 to 3. Note, a is equal to negative 1, b is equal to 3 because this is an interval, not an ordered pair. F of a would mean we need to find f of negative 1, so we can plug it in. Negative 1 squared plus 2 is 3. And f of 3, which would be f of b, is 3 squared plus 2, which is 11. I also went over how to do this with the calculator in class. I'm not going to spend time in here on the video doing it. If you're in class, you've seen how to use the calculator to get this information. But anyways, we then use this formula. The slope of the average rate of change is f of b minus f of a over b minus a, 11 minus 3 over 3 minus negative 1, which is 8 over 4, or 2. Therefore, the average rate of change of this function on the interval negative 1 to 3 is 2. So we drew this picture from negative 1 to 3 would be from negative 1 on the x-axis to 3 on the x-axis. That would be these 2 points. You also know the average rate of change, so we're talking about this secant line. And if you find the secant line using the typical slope formula, you'll find that the slope is 2. Now, we also did a secondary example. You can read through the example. I showed how to do it. I showed how to do this with the calculator, without the calculator. Well, I'm not going to go over it. That's just a snapshot of what we did. Then we talked about the concept of limits. Limits using a series of secant slopes to make a prediction about the instantaneous rate of change, also known as the tangent slope at point A. So I have some function drawn here of made up points. We want to know what's the slope at A. So this orange line represents the tangent line at point A. In order to find that though, since we only have 1 point, we can't. So what we do is we use a series of secant slopes. So we find the slope between A and D. And we find that it's 1.5. We then move closer to A and find the slope between A and C to be 1. We then move closer to A and find the slope between A and B to be 0.5. And as we can see is the slope's getting less and less, and it seems like it's converging closer and closer to 0. But we know that the slope of the tangent line is not 0 because 0 is a horizontal line. And the orange line that I have drawn here, which is the tangent line, is definitely not horizontal. Therefore, we can't say what the exact slope is, but we can use a series of secant slopes to predict that the line tangent at A has a slope that's between, well, 0 because we know it's more than 0, and less than 1/2 because that's the closest one as we get to it. So we would say, well, it's approximately 1/4. That would be a good estimate. But the idea of limits is we don't know what's happening exactly at the point that we're interested in, so we look at what's happening near the point that we're interested in and make a prediction based on that. We then went into how to find the instantaneous rate of change, also known as the slope of a tangent line. I had this picture drawn. I started to explain it. I didn't get to it.